First of all, thank you to everyone, the participants, for joining us, as well as the organization committee for the invitation. Much easier to jump on online than jump into a plane, although I do prefer the latter. And I just wanted to share a little bit of our research that we've been working with in terms of additive manufacturing with dental applications. If you need to get a hold of me, I'm sure you found the resources, but please feel free through old school email at ljkalman@icloud.com. And I'm also on social media as well as LinkedIn, as on Twitter and on Instagram as well. So just a little bit of background before we get started. So everyone's aware that there's differences in fabrication. When we're talking about 3D printing, we're talking about additive manufacturing. So we're talking about adding material in specific increments where we would like them. And in dentistry, this has really been limited to basically plastics and some wax. And we really haven't got into the ceramics and metals too much. It's still a little bit experimental, and we still have some regulatory hurdles. Having said that, our common workflow is definitely milling, which is subtractive manufacturing, otherwise known as computer-aided milling. And so this is really the workflow that dentistry has been in for the last few decades. So I'll just give you a little overview of a clinical case of how we do things, and I think that'll build a little bit of perspective on how we're trying to innovate in the additive manufacturing space. So on the left-hand side, we see an individual, and there was some sort of restoration here. And obviously that restoration is lost, and we have lots of options. I mean, we can do this chair side, but usually the ideal option is we do something indirectly, okay? And that would be something that's made out of a stronger material than just plastic. It's something that would be milled. And let's bear in mind that much of my research is in the medical device space. So what we're hoping to do in the medical device space is restore bodily function, aesthetics, form in a biocompatible manner. So how do we get from a broken, lost tooth to something that looks like this, that's going to kind of stand the test of time? So this is the pretty common workflow. Okay, this is the digital workflow involving milling and dentistry. So our number one thing we have to do is get some patient information, and this would be scanning inside the mouth. Okay, so we've actually scanned the tooth, and what you see there in the Bluetooth is we've actually did a digital design of the tooth, because it has to fit with the rest of the teeth, it has to fit with the bite, and this takes a substantial amount of time and some skill. Now that we've done that, how do we go from the digital design to an actual tooth? Here, we're utilizing a dental ceramic. This is called EMAX, otherwise known as lithium disilicate. And what we're doing is we're placing it in a milling machine. Okay, and here's where some drills come out, and they carve the tooth out of this block. And what you see is the end product here. Okay, now it does come out purple or pinky, and we still have to expose it to some temperature to get to the final product. In terms of metal, same thing. Okay, taking a metal disc, putting it in a milling machine, and getting out the metal components that we want. So that's the current workflow. So this particular topic I'll present is using additive manufacturing to see if we can develop a dental implant abutment. So instead of milling, additive manufacturing. So again, just a brief bit of background. When you're looking at dental implantology, the screw in the bone is the implant. The tooth on top is what we chew on, and the abutment is the interface in the middle. That's what we're talking about here. All right. So let's go over some methods and materials. So first and foremost, we have designed a new abutment, a novel abutment, and a process on how to make a tooth, and this has been patented. We've taken that patented design and we reached out to our partners at Idea Center. This is one of our industry partners here in London, Ontario, that works specifically with metal 3D printing. There we used the Fusion 360 software to tweak, make some changes to the digital model, and then we printed the abutment. And here we use dental grade titanium, otherwise known as TI-64. What do we use? We use the Restorative AM 400 laser melting system, which I will show you through a process of selective laser melting. So for those of you that haven't seen it, this is what it looks like. It's about the size of one of those sub-zero fridges, but the cost is significantly more. But that's essentially the printer we were using. So In the device space, the hardest part is to get a prototype or something to test out. And so this was our best guess, okay? It was taking existing components and putting them together and trying to come up with the concept, okay, so that we can test it further. What you're seeing on the right-hand side is this is kind of the samples that we would receive back from a dental lab. So you can see that the angles are totally different, the positions are different, so we have a quality control issue. But having said that, that's just the space that it is in dental device research. So the second part of the materials and methods was basically trying to design and print. We want something tangible to hold the abutment, okay? So we had to decide on lengths. We have to tailor this. So just like when you go to be tailored for a suit or a dress, you have to take measurements, you have to create the product and then try it on. So here we had to basically figure out pin projections, length, diameter, and test those before we decided on the final product. So the example here is, obviously this is still a block of titanium. We have to pick the proper length, the proper diameter to get where we want it to go, okay? This essentially is a final product, and what I'm doing showing here is that all these iterations had to be decided upon, because there is some distortion when you go from digital design to additive manufacturing. So that in itself was an exercise that we had to complete. If anyone has ever seen a build plate come out of metal printing, this was the build plate where the abutments come out, and I'm sure you can appreciate that the quality control is very high. There's still a lot of work to be done, and we'll talk about that. If you haven't seen what it looks like, I'll walk you through what it looks like, okay? So we have our powder bed, we have the laser doing its job, and those specific areas are where the abutments will be. And once the laser runs through, we can see we put down a little layer of powder again, and we start the process all over again. And something like this would probably take for the build 10, 12, 14 hours, okay? And then we get our final product. The third part of the methods and materials was, now that we have that abutment that you saw come out of the build plate, there's still a lot more to do, okay? So we have to heat treat them, we have to sandblast them, and then we have to get those threads on that we talked about. And once we've done those threads, we have to take this component and try with an implant, okay, to see how does it fit? How does it feel? Can we crank it down? Okay, let me walk you through some of that. So this is more of a visual exercise. So this had to be designed. This is actually the receptacle to hold the implant, okay? So this was designed and also additively manufactured in metal. So what you're seeing here is this is our little holder, and this is our abutment, and the pins are inside, and this is now within a vise. And then we brought over a die, okay? So old school die, and we're chasing the threads onto that shaft, okay? And there's our finished products, all right? So we have essentially a hybrid manufactured product, employing additive manufacturing and then subtractive manufacturing for the threads. How do we know it's done well? Well, that's a challenge, but it has to be per unit. And what we have here is a dental implant, and we're testing the threads just to make sure it's threading well, that fits well, so that we're going to torque it, it's not going to strip. And then each one went through a radiologic assessment. What we're looking for is essentially no gaps to seal. Is in an oral environment, if we have gaps, that's going to lead to some microbiologic issues, and it's going to compromise our end result. So in essence, the workflow was stage one of this research. How do we get from A to Z in a reproducible workflow? Okay, and that lists it out. So we have our images there in the workflow here. And for those of you, the PDF will be available, or if you have a phone handy, if you scan that, that will take you to the publication that lists everything that I mentioned in detail. So fantastic, we have a product. What do we do now? Well, now we need to test it, because two things we need to do. We need to crank it into an implant, and we have to see if it can withstand the process of temporization, making a tooth that I showed you. So this was our simulation setup. So here's the abutment we talked about. Here's the implant. And then here we basically have a custom jig that's fit in a metal housing. And then this is just an in-straw machine. So this is a load that's going to press down here until we get bending or failure. And we're going to take that measurement. Second part of the experiment is, let's crank it into an implant. So here's the abutment, here's the implant, here's bone analog that we housed, and then we have a sensor. And what we're doing is taking a standard torque wrench and just cranking it down and measuring it until we have failure. So basically the maximum torque that we had into the implant. So there's our data for our pin. And let's just draw a couple of conclusions. Okay, so the dark one is the additive manufactured, and the light one is the conventionally manufactured. These were the ones that were welded. And I think we can appreciate that the newtons are much, much higher for the additive manufactured. And that's what we would expect. Okay, the welding of titanium is quite unpredictable. And we know that this process of SLM is quite predictable and strong. How about the torque? Let's have a peek and talk about there. So the first thing I want to highlight here is this gray box. So when we're working with temporary abutments, which this is in that space in the medical device world, we need recommended torque within this area. Okay, so the dark is the additive manufactured and the light is conventional. And I think we can appreciate the conventional can withstand a higher torque. And it looks like most of our additive manufactured are out of the bubble of the recommended torque of temporary, maybe for one outlier. The problem here is that the driver was actually slipping within the abutment. So we had a design feature. So that will have to be redone. So what kind of results can we draw here? So we've employed a hybrid manufacturing approach for the abutment, okay? The abutment seems suitable, and that's checked with magnification and fit with an implant as well as radiology. And the data, I think we can pull that it can withstand the recommended torque, and the pin strength was more than suitable for the process of temporization. In terms of discussion, this is quite fun. So this is a preliminary investigation. We haven't gone into a clinical space at all, but there's definitely some inherent advantages of doing additive manufactured workflow for a dental implant component. And the first one is customization. I try to really highlight that. If you need to tweak something, the diameter, the length, it's so easy to do digitally, and then the output is pretty simple to do. If we're doing it old school, traditionally, that's much, much higher. You have a high consistency of products. Now the cost is unbelievable. So quite low once everything is matched up. Here we're talking about $10 a unit compared to about $240 a unit through the conventional way. And then again, the time is quite short. We're fortunate enough to have the manufacturing facility there. So it's just a matter of getting it there and back. In this day and age with COVID, if we're couriering something to a lab, it's going to take a lot longer. The challenges, well, I think anyone that saw what we were doing, getting that post-processing threads onto the shaft, that's a challenge. That takes time and that's difficult. So it'd be nice if we went to a complete additive manufacturing workflow. And then assessing whether or not an abutment is adequate, it does have some subjectivity. So it'd be nice to objectify what's there. So let's draw a couple conclusions. This is definitely an interesting avenue. We have efficiency. We have cost effectiveness and customization. Let's do some further research. Let's tweak that little driver so that we don't have slippage. Let's go into a clinical case. Let's do some maybe SAM, see where we're at. Maybe just pushing that research a little further. The testing that we did for the abutment, that was phase 2. That was literally just accepted for publication. If you would like to have a link to that, that is the QR scan code as well. So although I'm presenting, I have an enormous team behind us, and it's just always nice to acknowledge who was there. So first and foremost, the funding. Okay, so from my school, Schulich School of Medicine and Dentistry, as well as the ICOI, there's a lot of individuals that helped, our partners at Additive, our partners at Research Driven. And author disclosure statement, I do have financial affiliation with the product. So that's the dental implant world. That's what we've done. And I've showed you how we go from kind of getting a lost filling to a final filling. Well, how can we modify the filling world? So let me walk you through quickly here. Here we have a tooth missing a filling. Okay, we've prepped the tooth. So this person came in and is looking for an indirect filling that we chatted about. It's very simple to take a mold of just that tooth if we needed to replicate this. And that's what we've done here. This is just a chairside temporary. This is quite easy to do, a few minutes. Any dentist can do it. What we've went ahead is we've digitized that temporary filling, and we've sent that file off to 3D printing. And this was in chrome cobalt. We then cemented it on the tooth, and then we then assessed it radiographically. So what's the gist of this? What's so important? This workflow has literally bypassed that digital design component, which is very time consuming, very challenging, and very difficult. Okay, so that was literally accepted as well. So we'll have that out recently. The next one, how far can we push additive manufacturing? So we talked about one implant for one tooth. Well, in the real world, what if a patient is missing an entire arch of teeth? Okay, this is not uncommon. And so placing a few implants, we can then restore the whole arch. So this substructure that the denture fits on is typically made through milling, through subtractive manufacturing. Our current project is looking to see if we can do this through additive manufacturing. So this is the STL file of our model. This is the actual printed bar on our model. And then these are the prints that we just got back just after Christmas. So this is in progress and we're excited for the next steps. Well, at the very beginning of the introduction, I mentioned metals and ceramics, and we have not touched on ceramics at all. So let's jump in there a little bit. So if a patient comes in, and this is a digitized model, we can see that the two front teeth have already been prepped. Yes, they're missing a tooth, but please disregard this. If we have to create restorations and directly to fit over here, we still have a workflow of digitization and milling. Is it possible to 3D print those restorations? It is. And this is our partnership with Litho. So these are actually the interior restorations that we'll be fitting. Okay, this is zirconia that has been 3D printed, and we're going to be testing these out. All right, so the important part to remember is when you're prepping a patient for a restoration, it's almost reverse engineered. All right, so will this impact how you prep the tooth, and what kind of strengths do we have? We'll find out. If you'd like some information on the Kalman lab, here's a QR scan code. And thank you very much for your attention. If you have any questions, let me know. And I'm going to stop sharing the screen right about now.